Okay, if we combine our characteristic and particular solutions, this is the function that we get. If y of 0 equals -4 centimeters, I should have written y of 0 equals -4 centimeters instead of y sub 0. But if we agree that y sub 0 and y prime sub 0 mean the t equals 0 position and velocity, we're okay. Okay. Well, given these initial conditions, without going into detail, you just plug the initial conditions in and you get the following results. You get that C is 4 centimeters and the phase angle is -pi/2. That works out so that your solution is this. Now, I didn't write the -pi/2 here because that's only really important for the transient, for what happens near the initial instant. The important part of this solution is that the two frequencies, the two angular frequencies differ, so the two periods differ. This one goes faster than this one, which means this oscillation keeps overtaking this one. Okay? And that happens, well, every time 13.5 radians per second overtakes 12.2 radians per second on a reference circle. Okay, well, this is moving at 1.3 radians per second faster than that. So it's going to catch up at a rate of 1.3 radians per second. It'll catch up to 2 pi radians, and 2 pi radians divided by 1.3 radians per second. And that comes out approximately every 4.5 seconds or something like that. What you would get out of that, and I've got a y-axis here, I probably shouldn't have one, depending on the relative amplitudes of the sine function and the cosine function. If the amplitudes are the same, you would get something like this, because when the two are completely out of phase, they're going to, if they have equal amplitudes, they're going to cancel. Okay, so you're going to get a 0, and when they're not completely out of phase, or when they're completely in phase, you're going to have a maximum, and you're going to always go from cancellation to maximum to cancellation to maximum, and so forth, with the individual cycles in here. Okay, as I just alluded, it takes about 4.5 seconds for this to get ahead of this. Now you can work out just how much it is. It's 2 pi divided by the difference of the angular frequencies, 2 pi divided by 1.3. So we're going to go through the whole cancellation to reinforcement to cancellation in about 4.5 seconds. 12.2 radians per second is about a cycle every half second. So that in this 4.5 seconds, you're going to get about 9 cycles. And you can work all that out just again by understanding the reference circle picture and what a radian per second means and so forth. Okay, so you kind of have this envelope where we go from cancellation to reinforcement to cancellation to reinforcement to cancellation. Every cycle of that occurs in 2 pi over 1.3 radians, 2 pi radians over 1.3 radians per second, 4.5 seconds. Cycles of each of these functions, you get about 9 or 10 cycles in 4.5 seconds. So you have your individual sine and cosine waves coming in and out of phase, and I didn't try to sketch that at all. But the squiggles in here just mean that you have about 9 of these squiggles and about 10 of these squiggles in every cycle of the overall reinforcement cancellation, reinforcement, cancellation cycle. Now, in this case, though, the amplitudes aren't equal. Okay, so that this one has a greater amplitude than this one, so that when you have cancellation, that doesn't completely cancel this one out. It only cuts it about in half. So that our cancellation reinforcement cycle will go kind of like this. We go to maximum reinforcement and then we go to cancellation. Now, I didn't draw it quite right because when you have reinforcement, you're going to have a total of 12 meters, 0.12 meters of amplitude or of displacement from the equilibrium. And when you have cancellation, you're going to have like 0.4 meters. So this will actually be 3 times as wide as this. Now, you think about that, work it out, but you get something of this nature, but it's even a little wider or a little narrower here, or some combination thereof. Okay, that's what happens. Now, if the driving force is 12.3 radians per second, where the natural frequency is 12.2 radians per second, it's going to take much longer for this one to move a full cycle ahead of this one. Okay, it's only catching up at 0.1 radian per second. It's got to catch up 2 pi radians. It's going to take it about 62.5 seconds, 62.3, 62.28 and whatever seconds. It's going to take it about a minute. So we're going to go through a lot of cycles in a minute. We're going to go through 120 cycles a minute or so. So they're going to be like 120 cycles of the driving frequency, let's say, in a reinforcement, cancellation, reinforcement cycle. So it's going to be much more spread out. So it's going to look kind of like this, but much greater distance between the peaks of the reinforcement, between the valleys of the cancellation. And also, our amplitude is going to be much different. Okay, when you do this, this is negative, this is positive, but this is going to be much closer to this than it was. So that when you solve for A, you're going to get 2.5 meters per second squared divided by about negative 2.3 meters per second squared, pretty close to a meter. Okay? Since you have a meter of amplitude now in your particular solution, this is the particular solution, and only 0.04 meters of amplitude due to your natural oscillation, this is going to overwhelm this. You're going to get a much bigger amplitude, and the narrowing is going to be much less than it is in this case. Well, what you're doing is you're going from 13.5 radians per second, which is 1.3 radian per second difference, to a 0.1 radian per second difference. You're 13 times closer to the natural frequency if you drive it at this frequency, which gives you a much bigger amplitude because you have much closer to full reinforcement. And in the limit, as this approaches this, this approaches the exact value of this, this denominator is going to get smaller and smaller, which means your amplitude is going to get bigger and bigger. That's what we mean by an approach to resonance. Now down here I said that in the case of the 12.3 radian per second driving force, I said this is something like a meter, and this amplitude is still 0.04 meter. Okay, so again we see that this just makes a minor contribution to this, and we do get a much greater amplitude. In the limit, as this frequency, or this angular frequency, approaches the exact value of the resonant angular frequency, theoretically we get an infinite amplitude. Now in any real system, we do have dissipation of energy, so that's not actually going to happen. The system itself limits the amplitude. You start getting a significant drag force, limiting the nature of the resonance, but you can still get quite a bit of blow up in the amplitude of the combined function.